a couple more examples of working with these spring problems. So this time we want to calculate the work required to stretch each of the springs 0.5 meters or a half a meter from the equilibrium position, assuming that Hooke's law is okay, right? So we have a spring that requires a force of 40 newtons to be stretched 0.2 meters, and we want to stretch it to 0.5 meters. And then for the second one, this time it gives us the actual work necessary. It doesn't tell us the force, but it tells us the work um, to be stretched 0.2 meters away from the equilibrium. So it's a little bit different problem, right? So for letter A, this one's not too bad because we've essentially done this one. We're going to go ahead and we're going to start by finding the spring constant. Okay, and remember we have that the force is equal to a proportionality constant times x, which in this case the force is 40. Stretched 0.2 meters beyond equilibrium. And so just like we did before, we're going to divide by 0.2. And I believe that should give us 200 is equal to k. All right, just coincidental that it happened both times. And so our integral this time, we're going to have 200x. So that's our force function, kx dx. And we want it to go 0.5 meters. So that's going to be 0 to 0.5. If we integrate that, that's going to be 100x squared from 0 to 0.5. This should wind up being 25. So this will be 100 times 0.5 squared. All right. And this is going to wind up just being 25. Since we have meters and newtons, we're going to end up with joules for Newton meters. Now, this is the sneakier one. This time we have a spring that requires 50 joules of work, and we're going to stretch it 0.2 meters. All right. Now, in this case, our formula is the work is equal to the integral, but it actually gives us the work. All right. So for this one, we're going to say that 50 is going to be equal to the integral from 0 to 0.2 of kx dx. All right, so this is our force, right? But we just don't know what k is, but we know that the distance is going to go from 0 to 0.2. All right, so we just basically set it up a little bit reversed. All right, so if we evaluate this, we're going to get that 50 is equal to 1/2 kx squared, and that's going to range from 0 to 0.2. 0 is negligible, so 50 is going to be equal to 1/2 k times 0.2 squared. And that should work out to be, well, we have 50 is going to be equal to, this should wind up being 0.04, and half of 0.04 is going to be 0.08 k. And so if we divide both sides by 0.08, all right, that should wind up being 625 to be equal to k. All right, now this is the spring constant. That doesn't necessarily say that that's going to be the amount of work necessary. All right, but at least it gives us some help to be able to finish this off. Now, remember, ultimately we want to go ahead and stretch this 0.5 meters. And to do that, we're just going to take our integral. So our work is going to be our integral from 0 to 0.5. We know that the spring constant is 625, and we have x dx. All right, remember, we're just using force equals kx. We're not deviating from this. This is the force formula, or the force function. All right, we just plug it back in here. So when we integrate 625 over 2x squared, 0 to 0.5, substitute 0.5 in and square it. All right. And I know that that's going to be 0.25 times 625. So let me just figure that one out real quick. That one I can't do so quickly in my head. All right, so I've got my ultra sophisticated calculator here. So 625 times 0.25 divided by 2. All right, and I get 78.125. And that's going to be in joules since it's Newton meters. Okay. All right. So that's not too bad. Okay. So just illustrating how we can go through and try to set up some of these spring problems. Sorry if we have to go in the reverse order where we're given the work. All right. So In the next videos, we're going to be taking a look at a different application. So we're going to move away from force and we're going to move away from work. And we're going to start taking a look at fluid force instead. And we're also going to be taking a look at lifting. So we're going to kind of stick away. We're going to move away from just like these sorts of spring problems, go to a different type of work problem.